Hello, sir.
Yeah, let's start. Okay, so right, so the topic for the day I'm going to talk about is gravitational lensing and how Einstein became the household name that he is. So I will just share my presentation. Right, so this is what I'm going to do. Gravitational lensing, how Einstein became a household name. Right, so this is Einstein. I think all of you know Einstein.
Sir.
Yeah.
So first we have an introduction session. So if you
Right.
don't mind.
Okay. Yeah. Shall I unshare this?
Yeah, sure, sir.
Let's start the
Sorry for
introduction.
in trouble, sir.
It's okay.
Okay, guys. A very good evening, ladies and gentlemen. The secret of getting ahead is getting started. Thank you for joining us today. My name is Mosh and I'll be your moderator on this journey to the universe. I'm so excited to see you all here today, and I'm so happy to announce that it's a special day, very first day of Supernova, and we are so proud to do so. Astronomy is not just a word that defines the study of everything in the universe beyond the Earth's atmosphere. It is the key element for us to understand what are we. Astronomy compels the soul to look upwards and lead us from this world to another, and here we are going to do that. Today, we are presenting a sneak peek for all the astronomy enthusiasts for our first webinar of supernova and gravitational lensing and how Einstein became a household name. So, without a further delay, I would like to make some sure household works for better experience. So let's begin. Okay. First, I would like to highlight some of the do and don'ts during our webinar session. Guys, reminder to all the audience, please keep on your mic on mute all the time so that we are able to enjoy the webinar smoothly. Please give your full attention to this webinar. I'm sure all of you will be able to gain knowledge and learn more about today's topic. And last but not least, if you guys have any questions, please hold on to your questions because we'll be having a Q&A session at the end of this webinar, or you can just type in a Google form in the next chat box to post your questions here. Our group members will be monitored by all the postings in the chat box, so please don't be shy or hesitate to ask it. And finally, don't forget to remember that you all are going to be awarded with a valuable certificate of the participation. Thank you. Okay, that's all for the reminder. So kick off this webinar. I'll first hand over to our project manager of Supernova, Ms. Sadhanya Sundarlingam, for giving you all a warm welcome. Over to you, Ms. Sadhanya.
Thank you, Mosh. Can you hear me?
Yeah, you're audible.
Oh, thank you. Honorable Chief Guest Engineer Mr. 𝑬𝒏𝒈 and our lovely participants and our Executive Committee of Seds SLTC. Good evening, all. Actually, it's such an honor for me to get the opportunity to welcome you all on this wonderful day. And it's great to see you all here today. I'm here today to welcome you all for the first webinar series with the theme of gravitational lensing on behalf of our Seds community of Sri Lanka Technological Campus. And I'm so delighted to welcome you all to the fest. And supernova is actually not something that can be easily explained in 2 lines. So we got the proper insight to share more of its magic with everyone else who holds the same enthusiasm as us. So I do remember a statement which have been said by Mr. Ralph Waldo. He stated once that nothing great was ever achieved without enthusiasm and without sharing an enthusiasm. So, and I'm overjoyed to announce that we are actually doing that. And I'd like to say that we are going to do the best effort to make. Thank
Uh, thank you, Ms. Sadanya. Here we are. Let me tell me something. I hope you all do remember it. Tell me I forget. Teach me and I may remember. Involve me and I learn. Can you guess anyone whose this voice is? Yes. Yes, it is. Said by Mr. Benjamin Franklin. Learning by involvement is the greatest pleasure all the time, and today we have the chance to do it. We are so blessed by his presence today, because learning new things from randomly by ourselves may be fun, but involving and learning with someone who is at the next level at its blessing. To become a master of any skill, it takes the total effort of our heart, mind, and our soul working together in tandem. Let me introduce our guest of honor, Engineer Mr. 𝖕𝒕𝒕, who is reading the PhD in Astrophysics at University of Colombo and completed BSc Engineering Honors in Electronics and Telecommunication Engineering at University of Moratuwa, a researcher of cosmology, which includes gravitational lensing, dark energy, dark matter, and black holes. I would like to thank Sir for accepting our invitation and help us today. I think the wait is over. Yes, it's going to be happen. And I don't need to be disappointed. So without no further delay, let's dive into the webinar. So I would like to call upon Mr. 𝖕𝒕𝒕 for a place by his beginning. Over to you, sir.
Right.
Sir?
So yeah, I mean, you can hear me, right?
Yes, we can hear you, sir.
Yeah. Okay. So good evening to everyone. And so as I told earlier at the beginning, so I had some start at the beginning. So now I'll start it properly. So how Einstein became a household name. That is the topic of the day. That means I'm going to talk about the gravitational lensing and how it is affecting the astronomical community and the science at the moment. So first of all, I will share my screen with you now. So so that we as well, gravitational lensing and how Einstein became a household name. So Einstein is known by everyone. There's a reason for that. Now, for any genius, you call them Einstein, regardless of what they are doing or what they are finding, whether they are in biology or economics or whatever the case, you find someone very good at that, so then you call him Einstein. So Einstein became a household name like that. So the reason is he found something which just revolutionized the way we think of the universe. Now, I'll start with a brief history as well so that you will not miss a thing. So before Einstein, we had the Newtonian laws. I think all of you would have heard of that, F equals ma and the three laws, and then you take Newton's gravitational law. So all these things will describe the universe to a certain extent. For example, if you look at Newton's gravitational law, Newton said there will be a force acting upon two bodies which are close to each other. Now, for example, think of the Earth and the Moon. Because of the gravitational force between the Earth and the Moon, these objects are orbiting each other. But he thought of that as, now, if you can remember, the apple, when Newton said, okay, apparently, allegedly, we don't know whether that really happened or not. So the idea is he got the idea of gravitation used by looking at the fall of an apple. So anyway, so the thing is, all these objects which are fall into the earth and all, that is all due to the gravity. And then he formulated his law of gravity, which is a very simple equation: F equals G m simple m divided by r squared. G is the Newton's gravitational constant, and m and simple m are the objects, the masses of the two objects, and then r is the distance between those two objects. So that is a very simple rule. And then up to the end of 19th century, okay, within 18th century, right? Okay, whatever. So let's say up until 1890, 1900, around that time, people were all happy with the Newtonian theories and all, because they can understand a lot of things. And people actually thought we have found everything that you have to find in the universe. And then there were some discrepancies. Now, for example, the motion of the Mercury, one of the planet which is closest to the sun, the motion of that cannot be explained 100% using the Newton's gravitational theory. So then Einstein was thinking of all these things, and then he came up with the special theory of relativity in 1905. That is around 117 years back. So in the special theory of relativity, he was talking, he postulated one important thing. That is, the speed of light is a constant. All this time in the Newtonian physics, we had this absolute time. That means if something happens somewhere, that thing will be noticed everywhere. But if you look at this, think of the light rays coming from sun to the earth. The light rays coming from sun to the earth will take approximately 8 minutes. Okay, so that means if the sun to disappear right now, okay, it's evening now, so you can't see the sun. Just imagine if the sun to disappear at 5 p.m., you will notice it only after 8 minutes, because you will not be able to see the sun has disappeared until the light from the sun will not reach us. So that means there is no absolute time. Time is relative. Time is relative to each person. So the time here is one time, and time in Mars is another time. So likewise, two events which are happening at one point cannot be said to be happening at the same time, because time is different. But one thing is sure, that is the speed of light is the constant. For example, the speed of light is 300,000 kilometers per second. At that speed, the light from the sun will come to us within 8 minutes. At that speed, the light rays from Proxima Centauri, which is the closest star to us, will come to us at 4.2 years. So likewise, the speed of light is the constant, but there is no absolute time. So that is the summary of the special theory of relativity. Right. So now we have the theory of relativity. And then in the theory of relativity, or even before the theory of relativity, people thought something like this. If gravity is an attractive force, if a light beam goes closer to an object, let's say near the sun, that light has to be attracted by that object. So that light beam has to be attracted by the object. That is the idea people had even prior to the theory of relativity, and they even calculated that. Assuming light to be a particle with a small mass, as the mass will cancel off in the Newton's gravitational theory, they actually found a value for the bending angle. They had that value, and then with the special theory, they see that, okay, according to special theory also, the light bending will happen. But still, they did not have the exact answer until 1915. That is when Einstein introduced the general theory of relativity. So in the special theory of relativity, gravity is not there. It's all about the speed of light. But in the general theory of relativity, we talk about the gravity as well. How gravity is curving the space-time. So space-time curvature is part of this Einstein's theory of general relativity. And I think you have a brief idea about the space-time. So I'll just introduce that one as well. So think curve the space-time around that object. And remember, with the special theory of relativity, Einstein disregarded the concept of absolute time. So we have three spatial dimensions, x, y, z, and time. So all these four dimensions will be combined together to make the space-time. So what general relativity says is, around a massive object, space-time will be curving. For example, around Earth, the space-time is curving. In that curved space-time, the moon will try to go in the shortest path, we call it geodesic, and that shortest path happens to be a curve around the Earth. And similarly, around the sun, the shortest path will be traveled by the Earth, that is the orbit of the Earth around the sun. And when the object becomes more and more massive, it will curve the space-time more and more. That's the idea. Now, if you look at a black hole, it has a huge mass, and because of that, it will curve the space-time massively. Because of that curvature, even light emitting, or not light, we will not call it light, let's say photons. Any photon which is trying to escape from the black hole will not be able to escape because of that curvature of the space-time. Right, so that's a different topic, so we will not go into that too much. So now, Einstein, from his general theory of relativity, predicted a value for the bending angle near the sun. That's what Einstein did, and he did it in 1915 or 60, around that time, when he introduced the general theory of relativity. That was a prediction from the general theory of relativity, but there was a prediction from the Newtonian theory as well. So people or the scientists wanted to see which one is correct. So in 1919, there was a solar eclipse. In 1919, there was a solar eclipse. So people or the scientists wanted to find out whether the light beams are deviated due to the mass of the sun. So now, for example, if you look at this, so here you can see, this is the, so they were measuring the movement of stars and whether the path of the star light is bent. So this is the actual position of the star. You can measure it without the sun. And then when it comes closer to here, due to the mass of the sun, the light rays will get attracted, or it will be going to the gravitational well of the sun due to the space-time curvature, and then it will change its path. So when we observe it from here, you will see the star to be here. That is the apparent position. So from the actual position to the apparent position, there will be a slight delay, not delay, a slight bending. So that bending is there were two values for this bending, from the Einstein general theory of relativity and from the Newtonian physics. And Arthur Eddington, he went to I think somewhere in Canaries or someplace, okay, I can't remember where. He went somewhere close to African coastline. He went and he observed this solar eclipse, and he got the measurements, and he found out Einstein's value is the one which matches the best of the observation. So the observations are matched by the Einstein's prediction. That's how Einstein became a household name, because everyone started to see Einstein has found something new that will explain the universe much better than the Newtonian salesman. So that is how Einstein became a household name or a global celebrity in 1919. And then because he predicted this bending angle properly using his general theory of relativity. Right. So that is the basic idea as to how Einstein became a household name around the world. Not even in USA. He was actually in Germany and Switzerland, and then he went to Princeton in USA. So anyway, he was well regarded even those days. And now he's a household name because everyone knows Einstein. Not because he found something like this, like gravitational lensing, but he found it and he became like, people thought of him as a genius. That's why all the geniuses, all the people are called an Einstein nowadays. Right. So that's a brief explanation about the 1919 solar eclipse and what is actually happening here. Now we will look at some ideas about gravitational lensing. So Einstein predicted this gravitational lensing, and then we were able to observe this using the solar eclipse, that light is actually bending near a sun, near a star. But then when you want to observe these things in detail, like now people wanted to see whether we can observe other things being bent. Now remember, these days, the universe is only the Milky Way, right? In 1950s or 1920, people did not know that there were galaxies outside the Milky Way. That was found in 1929 by Edwin Hubble. He found that other globes, so small smudges that you can see in the sky are actually other galaxies which are further away from the Milky Way. So then our universe got bigger, because it's not only the Milky Way, but we have a lot of other galaxies which are in the universe. So then, but the gravitational lensing, people thought it's not possible to do the measurements. Let's say you can't measure the light coming. Let's say, think of some other star in the large magnetic cloud, that is one of the closest dwarf galaxies closer to the Milky Way. So then if you want to see light coming from that object, or light coming from a star in large magnetic cloud, so you will not be able to observe it here, because the observational facilities are not there. But then again, in 1930s, a scientist called Fritz Zwicky, he said that, well, we might not be able to observe the light coming from a star, but we should be able to observe the light coming from a further galaxy. And that further galaxy, if there is some intermediate galaxy in between, the light rays coming from that further galaxy will be bent. We should be able to observe it. So he proposed that idea in 19. But still, people thought we don't have any observational evidence. So the field of gravitational lensing went dormant for some time until this observation. In 1971, if I can remember properly, we observed two quasars. Okay, I think I need to give you an idea about what is a quasar. Quasar is an active galactic nucleus, so AGN. Active galactic nucleus is when a black hole or a supermassive black hole inside a galaxy, when it feeds, it can give away jets of light. So that is what we call a quasar. So when that supermassive black hole is feeding on the material around it, it can give away these jets, and that is called a quasar. So that's the brief idea of a quasar. So people were observing quasars in the universe. Not all the galaxies are having active galactic nuclei. So some are dormant. Now, for example, if you look at Milky Way, our supermassive black hole is dormant. It's not feeding that much at the moment, but there are black holes which are feeding extensively. So those are the quasars that we can observe. Now, people observe two quasars. In the middle of this image, you can see that there are something pretty similar. So we observed two quasars. We call them Q09515661. So these two quasars were having the same brightness, and they look pretty adjacent to each other. The distance between those two are much smaller, and they are having the same spectrum. Actually, this is not the same spectrum coming from that. This is kind of a spectrum. So two quasars which are close to each other having the same spectrum is something very suspicious. It's not practically possible or probabilistically possible for two quasars to be in close proximity to each other with the same spectrum. So then people realize that actually this is not two quasars, but this is the same quasar, but which is gravitationally lensed. That means we are seeing two images of the same quasar because of an intervening galaxy or intervening mass distribution. So here there is some kind of a mass in the middle that we cannot see, maybe a galaxy or a galaxy cluster. But whatever we are seeing here are not two quasars, but that is a single quasar. But the light from that has been gravitationally lensed, and you can see two separate instances. So that is the twin quasar that we observed in 1971. So now the gravitational lensing was actually observed, and since then we are observing it very to a great extent. I'll give you some examples of gravitational lensing later as well. So this is the beginning of the idea of gravitational lensing as a practical situation. Like now, all this time people thought this is a theoretical thing, but now we can actually observe gravitational lenses. That's the beginning of a new era of cosmology, right? So not only two images, you can have, okay, this is a spectrum, you can have four images. This is what you call an Einstein cross. So in the middle, you can see the intervening mass, which is a galaxy cluster or a galaxy. And then you can have four images as well. Usually you will have two images, but sometimes you might have four images. But in very rare occasions, if the intermediary galaxy as well as the quasar is happening to be in the straight line, or they're like straight back to the other one, then you will be able to see this Einstein ring. So the light coming from the faraway galaxy will be distributed like in a ring. So that is what you call an Einstein ring. So these are all actual observations that we have done using the Hubble telescope. And now we have a much better telescope in the sky. I'll talk about the James Webb in a little while as well. So now gravitational lensing has been proven beyond any doubt that due to some massive universe, the light coming from faraway objects, light or the photons coming from faraway objects will be bent like this. So that is the idea of gravitational lensing. And then I will explain how this happens. Now here, this is the galaxy that we have. So this galaxy will be emitting light. So it can be a quasar or the light directly from the galaxy. So here we have an intermediary galaxy cluster. So between the galaxy that we are observing and the Earth, that is us. So here we have a mass distribution. So due to this mass distribution, the light coming from this galaxy will be bent like this. And then not only bent, they will be forming different images as well. So these are the lensed galaxy images. So in the normal case, you will have two images, or else you can have four images. And in very extreme cases, or in ideal cases, we can have an Einstein ring as well. So that is how the gravitational lensing is happening. And there are three versions of gravitational lensing as well. This one that we observe as two images, four images, or an Einstein ring is called the strong gravitational lensing. In that, we can actually observe different images or a ring-like structure. But then there is weak gravitational lensing. That means the intervening galaxy mass cluster is not powerful enough, or the light rays are coming not that closer to the galaxy cluster in the middle. You will have arcs-like structures. So these arcs, entire galaxies will be distributed as arcs. And I will show you some images of that later as well. And that is what you call the weak lensing. So strong lensing is there, weak lensing is there. And the third one is called the micro lensing. Micro lensing happens, any light rays coming from faraway universe, if it happens to come closer to one of the stars in the Milky Way or some galaxy cluster or galaxy closer to us, the light coming from the object which is behind will again be enhanced due to the gravitational lensing of the star of the Milky Way. And that is also, then you will be able to see some faraway objects which are not possible to see without gravitational lensing. And then that is the micro lensing, that is being able to see objects which are not possible to see using the magnification effect of the gravitational lensing. Right, I think I could not mention you that earlier. A gravitational lens, further to make in different images, they will magnify the light or the photons coming from a faraway galaxy. That's why we actually call it the lensing, because the light will be magnified. And so this magnified further away, we will be able to observe that as the light coming from those objects will be gravitationally lensed, and then you will be able to observe them at Earth, right? And this is how the lensing happens, and how the light rays coming from faraway galaxies will be bent, as well as they will be forming different images. And now we will look at an lensing diagram or schematic diagram that you have. So here, I will not go into any technical details as it is not the idea here. I will just observe what is happening. In this diagram, I will just tell again what is happening here. Now, this is the observer, that is us. And this is the lens, there is some galaxy cluster or something in the middle. And this is the source plane. This is where the light rays are coming. So we denote the distance as dl is the lens to the observer distance. ds is the lens to the source distance. And dls is lens to the source distance. Those are the three distances that we have in gravitational lensing. And then any light ray which is originating from here will be coming towards us. And here we have the intervening mass. And due to that intervening mass, the light rays will be bent. So because of that bending, you will be able to see two apparent images. So here, this is the actual light ray which is coming, and here it will bend. So once it bends, this is like the refraction that we have in the, I think you know about the refraction. In the refraction also the light rays will bend. In a similar manner, light rays will bend here, and then you will be able to see this object in this location, as well as you'll be able to see from the other side the same object in this location. So this is how we observed the twin quasar. So if I went back a bit, so these two things are not a different thing, but it's the same thing. Because of the gravitational lensing, as it happens here, you will be able to see two images of the same thing. And then you can do a lot of calculations from that. And the image, one image will be actually magnified, another one will be demagnified. So those are some technical details which I don't know to go detail again. So, but the thing is, you can just keep in your mind, the images will be magnified so that you'll be able to see them as well. And also there is another effect. These two light rays which are coming from this faraway galaxy will be coming at different time intervals. That is what we call gravitational lensing time delay. The difference arises from two reasons. One is the light rays, some light rays might come closer to the intervening galaxy. We call it the B value, or the, there's this value which has escaped my mind now. So this is the distance. So if the distance is closer, okay, this is called the impact parameter. This distance is called the impact parameter. So these light rays will travel in two pathways. So as light is having a finite speed, if they are traveling in two pathways, they will be having different arrival times. And apart from that, due to the gravitational potential of this object, if a light ray becomes too closer to the mass cluster, then it will be coming closer. It will be coming slower. Now, if you can remember Interstellar, I think most of you would have watched the movie Interstellar. Now, in that planet, where you have that, if you can remember, there was a planet orbiting a black hole. So in that planet, 1 hour is equal to 7 years on Earth. Is it possible? Yes, it's possible, because that movie is based on actual facts. It's possible because that planet is much closer to a black hole, and it is within the gravitational well of the black hole. So black holes are, as I told you earlier, will be in the space-time around that object a lot. Therefore, the time will go slowly near a black hole. That's why 1 hour, okay, that's why 7 hours on Earth is equivalent to, let's say, 1 hour near the black hole, because of that gravitational potential. And the same effect will be applied here. If the light ray goes closer to the object, then it will be bent. It will not bend. The time of the light ray will decrease. Therefore, there will be a time delay. So we can measure those time delays as well. If you have a variable source or a variable quasar, then we can actually measure the time delays, and making use of that, we can do a lot of important calculations as well. Right. So that is how the gravitational lens in a technical way is happening. So we have these angles. The alpha is the angle from the apparent location to the actual object, and then theta, those are the maybe angles and also you don't have to worry about it too much. Those are technical details. If you are going to research in gravitational lens, you will have to study these things. But in a summary, gravitational lensing will make different images of the same object, and those images will be magnified, as well as the light rays coming from those images will have a time delay as well, or a different arrival time, so that you can do some important calculations. So in a very simple sense, that is what gravitational lensing is. And then this is an image. I think you would have seen it recently. It was released in last 12th of July. This is the first image released by JWST, or James Webb Space Telescope. So here you can see a lot of gravitational lensing effects. So here in the middle, we have something called SMSCS 0723. That is a huge galaxy cluster that we have. Because of this galaxy cluster, a lot of other galaxies far away or far behind of this galaxy cluster will be having these shearing shapes. These are all examples of gravitational lensing. Can you see that the pattern? All these shears are like, if you take the perpendicular to all these shears, they will all center around this galaxy. So because of this galaxy cluster, so because of the gravitational potential of or the gravitational force of this galaxy cluster, all the faraway galaxies. Now, all the reddish ones are okay. I think I have to give you that idea as well. So you can see all these galaxies which are having a shear shape are red. Any idea why is it? If you look at this galaxy, it's a proper galaxy. And here you can see all the normal galaxies. They are all bluish and something like that. But all the bent galaxies or sheared galaxies are red. That is because redshift. Any light coming from far away place will be redshifted. So redshifted means the universe is expanding. Due to the expansion of the universe, light rays coming from far away places will be expanded. So when a light ray is expanded, you can see that its wavelength will increase and the frequency will decrease. So when the frequency is decreasing, light will go towards the red side of the spectrum. If the frequency is increasing, then it will go to the ultraviolet side of the spectrum. But when the frequency is decreasing, it will go to the reddish side of the spectrum. So that's why all these faraway galaxies are looking reddish. That's because of the redshift. And all these faraway galaxies, the light coming from faraway galaxies are bent or due to the gravitational lensing effect of the larger galaxy cluster in the middle. So this is a very good example of gravitational lensing. Right. So now I think I gave you a brief idea about the gravitational lensing. Now let's see what uses we can have from that. Any idea as to what we can do with gravitational lensing? So I'll tell you. So you can ask questions. So in a little while, I should be able to finish the main lesson or the main program. And then after that, we can go to questions. I think most of you will be having a lot of questions regarding lensing as well as other things. So I will dedicate some time. So we have about 15 more minutes. So even more than that. So the uses of the gravitational lensing is, using this, we can find mass distributions of the universe. As we know, due to a mass, the light rays coming from behind are bent or having these gravitational lensing effects. We can find the mass distribution. And this is one of the ways, or this is like the main way we found the dark energy. Now, dark energy is not dark energy, dark matter. Dark energy is a different thing. Dark matter. So, in the universe, we have normal matter. So, in the stars, interstellar medium, and other dust clouds, gas clouds, and planets, all the stars, they all comprise of the normal matter. But they are only about 5% of the entire universe. But there are about another 25% of matter which we can observe through their lensing effects and all, because we can see there is a huge, now let's say for example, if you look at just the visible matter in this diagram, they are not enough to bend the galaxies, the light coming from galaxies this much. There has to be something much more than what we can observe in order for the light from behind sources to be bent this much. So because of that, there is an indirect evidence of the existence of dark matter. That means some kind of matter which is not interacting with normal matter, but we can observe their gravitational effects. That's the dark matter. And as I told you about dark energy, I'll tell you that as well. Dark energy is another energy source within the universe, which will make the expansion of the universe accelerated. For example, once we found that universe is expanding, 1929, Edwin Hubble found that universe is expanding. So we found the expansion rate, and then we went backwards, we backtracked, and we found out 13.82 billion years back, from a single point of a singularity that we call the Big Bang singularity, the universe came to life, right? 30.82 billion years back, universe came to life, and since then it has been expanding. And then people wanted to find out the expansion rate or the deceleration, because if something was accelerating, something was expanding for 30.8 billion years, it has to lose energy and it has to decrease the expansion rate. That was those researchers were conducted in 1997 and 1998 by Adam Rees and Sean Palmer and those scientists. And then what they found is the universe is not decelerating, but the universe is accelerating. Since about 7 billion years back, universe has been accelerating. So that acceleration is due to the dark energy. So that's the idea of the dark energy and how we found it. And dark matter is a different thing. It's a kind of a matter that we have in the universe. And for the universe to develop the structures, like development of the galaxies, very early galaxies, like 13 billion-year-old galaxies, or even prior to that, galaxies were being born. Now, from the James Webb, we were finding out that galaxies were there about 200-300 million after the Big Bang. But how did galaxies happen to be after 200-300 million years after the Big Bang? It's a mystery. So the only way it can happen is there's a huge dark matter distribution, and that dark matter distribution helped in making those galaxies, and we call these galaxies are having a huge dark matter halo around that, which we cannot see, but which will, the gravitational effects of that dark matter halo is apparent. That's how we see all these lensing effects and all, because the normal matter within this galaxy cluster is not enough to make this much of lensing effect. Right. So that is one thing. We can find out the matter distribution in the universe, in which area you have more matter, in which area you have dark matter, in which area you have galaxy clusters and all. That is one thing. And then you can find another thing using gravitational lensing time delays. You can find the Hubble constant. Hubble constant can be found in different ways as well. And using the gravitational lensing also, we can find an independent value for the Hubble constant. So likewise, gravitational lensing will have a lot of users of that. So people are researching a lot in gravitational lensing because we can find out a great deal of things about the universe using that. Right. So then I think that's all I have to talk about the gravitational lensing. So we have 10 minutes. So if you want more time, I'll get some more time for the questions. So I think you have an idea about gravitational lensing now. As I told you, I don't want to go into the technical details, but I just gave you a brief idea about how Einstein discovered or proposed gravitational lensing, and how he was proven by Eddington in 1990. One more thing regarding that, there is another movie called Einstein and Eddington. Go and watch it if you haven't watched it already. It gives you an how these things are found in 1990. The movie is Einstein and Eddington. You can watch that. And then since then, gravitational lensing lay dormant until 1971, and until we observed the twin quasar. And since then, this research area has been expanding more and more. A lot of people are researching this because you can find out the mass distribution and a lot of things in the universe from this. So even using Hubble, we were using the Hubble data until now, but now we have the JWST data as well. From that, there will be a lot of things now. Remember, Hubble or JWST is not only about images, beautiful images like this. Inside these images, we have a lot of data. Those are the spectrums or things that we are observing. The image is good, it's beautiful, you can admire the view and all, but spectrums are the ones which are important to us. Now I told you this is a spectrum coming from this light spectrum. So you can see that based on different elements and all those things we have, the spectrums will vary. So from these spectrums, we can find out what elements are there in the universe and what elements are there in the intervening gas clouds and all. So there are a lot of things we can find using the data in these images. Not only the beautiful image, but we can make use of the data within that. So that's what we do as cosmologists, identifying all this data and then analyzing them and finding out what's happening in the universe. Right. So then that's it. That's all I have to say in the main session. And then I'm open to questions. So if you have any questions, you can ask now. Right, any questions? I think there is the program organizers can let me know any questions if there are any. Yeah, Mosh, do you have any questions from the participants?
Yes, sir. We have made some questions in here. If you don't mind, may I?
Yeah, you can ask them.
Yeah, the Google form. Yes, sir. The first question is it possible to observe strong gravitational lensing with an armature telescope?
Yes, I have showed you pictures. Those are all strong gravitational lensing pictures. The twin quasar as well as the Einstein cross and the Einstein ring, all those things are examples of strong gravitational lensing.
And
those are all actually observed by Hubble. And then the JWST image, that is also strong lensing. You can see that all these arcs and all, that is also a good example of strong gravitational lensing.
And the second question is, what is the first confirmed visual observation of gravitational lensing?
That is the twin case. Okay, if I look at the very first one, that is the 1919 solar eclipse, where I didn't prove that Einstein is correct. That is the first gravitational lensing observation using the stars of Pleiades and the sun. The gravitational lensing of the sun was used to observe the stars of Pleiades behind that. So that is the first observation. And after that, the 1971 twin quasar was the second observation of any stellar level, not the stellar, galactic level. That's a stellar level observation, the 1919 observation, and 1971 is the galactic level, first galactic level observation.
The third question is, what's the role of the dimension in the theory of special relativity?
What's the
role of the dimensions in the theory of special relativity?
Role of the dimensions means, okay, in the special relativity, I told you, before the special relativity, the Newtonian physics, we had three spatial dimensions, x, y, z, and time separately, absolute time and the space. But Einstein, with the special relativity, combined these four dimensions into space-time. So in the space-time, we have three spatial dimensions, and the time, they are all like together. We can't take them separately. I think those are the dimensions, if I get the question correctly. Otherwise, that person who has asked the question can clarify me as to what exactly is asked.
Please explain the 1AX and SN2102Z.
Okay, I want the question again. Explain
Yeah,
what?
so please explain the 1AX and SN2012Z. Yeah, that's
I don't get the question. Explain SN. SN means a supernova. 2012 set.
I don't know, sir.
I'm not clear about that question.
Okay, sir. I'll move on to the next question, sir.
That person who asked the question can.
If anyone
like the question again,
who asked
in
this
verbally.
question, please unmute yourself and ask yourself, please. If anyone here? Okay, Vasant. Can you please unmute yourself, Vasant?
Sir, am I audible?
Yeah, you can audible, Vasant.
Sir, my question is gravitational lensing is a method. Okay, I understand that gravitational lensing method. Is it useful to measure the value of Hubble constant accurately? Because we are using Cepheid variables and supernova for the Hubble constant measurement, but it is not accurate. Not that much accurate. Can we use the gravitational lensing for that measure of Hubble constant, sir?
Yes, I would not say the values that we have are not accurate, because actually we have two values at the moment. One is from the supernova, that is the supernova explosions. That value is somewhere around 72, that range. And the other one is from the Planck experiment, from the cosmic microwave background radiation, that is somewhere around 67. So we have something called an Hubble constant controversy. That means we are having two different values to the Hubble constant at the moment. It's not anything about the accuracy. The both values are accurate, but we want to know which one is correct. So being accurate and correct is two different things. But gravitational lensing can be used as the third independent method of finding Hubble constant. People in other areas now, actually a lot of people in post-month in UK are studying about gravitational lensing. There's an experiment, there's a research called 𝑬𝒏𝒈. So that's about how to find gravitational lensing, how to find gravitational lensing to find how to use the gravitational lensing to find the Hubble constant. So yes, we are still using that, but still the time delay measurements that we are having some problems. So because of that, the value of the Hubble constant is not refined too much. But as you said, we can use it as a third independent way of finding the Hubble constant. And in the future, of course, we will have a proper idea about the Hubble constant and the solution to the Hubble constant controversy. Actually, in 2018, I went to Berlin for a conference. That conference was called the Hubble constant controversy. So the people from the Planck group and the supernova group, that Adam Riess, he was the person who found out the dark energy in 1998 using the expansion of the supernova and all. Actually, they were all present in that conference. So at the end of the conference, people could not agree on a proper H0 value. And still there are a lot of doubts and debates going as to what is happening. But in the future, I think we should be able to find out what is the actual value of the Hubble constant. It's actually ongoing at the moment.
Thank you, sir.
The next question is, in the concept of gravitational lensing is statistical analysis involved there. If there is any involvement of statistical being of statistics students, how can I conduct study, or how can I involve myself regarding this kind of study? I think, sir, you answered this question earlier before, so I'll move on to the next question.
Yeah. Okay.
Having use of secondary lens plane can we use the gravitational lensing concept as a gravitational telescope so that we can see much farther objects?
So that's what we are doing. So as I told you, we can observe further objects due to the gravitational lensing effect of nearer objects. So some things which we cannot see normally can be observed using gravitational lensing. So that is how we use gravitational lensing to observe further stuff. So that is a gravitational lensing telescope. You can simply say that. Correct?
The person who asked this question got it, right? Yeah.
I think it's okay.
Yes. Okay, sir. The next question, my question is that when we get an object image after gravitational lensing, we will get the next exact location of that object or no? Can I repeat myself, sir?
Exact location with respect to what? So when you say exact, it has to come with respect to something. So what we observe is, let's not say exact location, but let's say the location. So we can observe the location of that object in the universe. So they will be bent. Though bent means I'm talking about smaller angles like very small angles. So then the location of the object will not be moved too much, but we can see there is a measurable lensing effect that is measurable.
If gravitational lensing a good way to research? Sorry, sir. Is gravitational lensing good way to search for negative mass?
Negative mass is a theoretical concept at the moment. So yes, in a theoretical manner, we can think of something like that, but gravitational lensing offers due to positive mass. So let's say some mass. Well, you can research on that area. It's not, there are a lot of new areas. As we don't have any actual observations of negative mass apart from theoretical concepts, so that I would say we have to wait until new observations are available.
And that's it. That's all for the day, sir.
That's all right.
So
Anyone else, if you have anything, you can ask.
We move on.
Yeah, you can continue.
Yeah, we move on to the next session. Thank you so much, sir, for clearing our doubts. In such a pleasure for us to learn with you. And great, isn't it?
Right, so thank you very much for inviting me to the session. I hope everyone had a productive session, and this is a very good research area. If you are going to research in the future, there are a lot of new things that you can find, because university is always fascinating us with different things. So in gravitational lensing also we are learning a lot of new things. So if anyone is interested in continuing higher education in astrophysics or astronomy, cosmology, you're all welcome to do so, because it's a really interesting area.
Great, isn't it? We learn a lot. Actually, I hope everyone here has been got the universe for a while. It's actually a pleasure to be here with you, sir, and we would like to convey our heartfelt gratitude. So let me welcome Ms. 𝑬𝒏𝒈𝑮𝒈, Observation Division Secretary, for conveying the heartfelt thanks. Ms. 𝑬𝒏𝒈. Ms. 𝑬𝒏𝒈. I think she's gone. think she's gone somewhere. So,
Okay.
The best and most beautiful things in the world cannot be seen or even touched. They must be felt by the heart. Thank you is one such a prayer among them. And with that, I would like to thank everyone for being present here today on behalf of the Observation Division of Seds SLTC. First of all, I would like to extend my gratitude to our chief guest, Engineer 𝖕𝒈 for delivering this fascinating session that I am sure everyone enjoyed. We thank you for taking time for your busy schedule to attend the event and nurturing the participants with your knowledge. Also, I would like to extend my appreciation to I would like to also thank the executive committee member of Seds SLTC for their guidance, the organizing team and volunteers for working hard for the past few days to make this webinar successful, and all our valuable participants here with us today. It is an honor for me to get the opportunity to thank you all. Once again, my appreciations goes to everyone who attend the webinar with great enthusiasm. Have a great evening. Thank you.
thank you, Ms. Prabodhini. And one more thing, if you want to follow Mr. 𝐕𝒈𝒈, you can find him on YouTube at Astrophysics. Do not forget to subscribe, right? We hope you gain the best out of this session. Thank you so much for a wonderful audience tonight. So that's it. That's for the day. That's for the day, folks. It's been a great evening with you all. Stay tuned until your next webinar. This is your Mo signing off from SUPERNOVAE. Good night, take care, and bye-bye. And stay safe. Thank you.